Hey there, it's Shannon Myers, and we have come to the second part of our course, which focuses on determinants, general vector spaces. So we looked at vector spaces in Rn and a tiny bit of the vector space, which consists of the M by N matrices. And then we'll also look at matrix representations of linear transformations, which is awesome. Okay, so let's start off with section 3.1 on the determinant of a matrix. Cool? It turns out that every square matrix can be associated with a real number called its determinant. Historically, the use of determinants arose from the recognition of special patterns that occur in the solutions of systems of linear equations. So our first definition here is the definition of the determinant of a 2x2 matrix. The determinant of the matrix A equals A11, A12, A21, A22 is given by, so you can either write DET, parentheses, whatever your matrix is named. You can also write these bars here, which, when you're dealing with the real numbers, it means the absolute value. But when you have a matrix in there, it means the determinant of that matrix. And it ends up being equal to A11 times A22 minus A12 times A21. Groovy? All right, so note in this text that we're using, this workbook, and many texts, the determinant of A, I mentioned it up there, and using this notation for the determinant of A are used interchangeably to represent the determinant of a matrix. So in this context, the vertical bars are used to represent the determinant of a matrix as opposed to the absolute value. All right, so let's look at an example 1. Example 1 calls on us to find the determinant of A and the determinant of B. So all we do here is what? Beautiful. Determinant of A is equal to -1 times 7 minus 4 times 11. Cool? And so what will we get for the determinant of A? -7 minus 44, which will be -51. Good? All right, go ahead and try the next one and see how you do. And then, okay, why don't you pause the movie and try the next one and see how it goes. All right, let's see how you did. I'll use this notation this time. So the determinant of B would equal to what? Awesome, 21 times 10. Minus, now be careful of your signs. It's easy to mix them up when you're doing the computation here. So our determinant of B is going to be what? 210. We got 3 minuses, so it's going to be minus 18. And so our determinant of B will be equal to, beautiful, 192. Okay, here's something that's a cool factoid. It turns out that A inverse is equal to 1 divided by the determinant of A, if it's non-zero, times A22, negative A12, negative A21, and A11. So what happened here? The main diagonal entries are switched the other entries are multiplied by -1, or you do the opposite of them. Cool, cool? All right, so remember, main diagonal starts at the top left and goes down to the bottom right. So let's use this method to try it out, all right? So A equals -1, 4, 11, 7. So A inverse would equal to 1 over, so the determinant of A is found by, good, multiplying -1 times 7, and then minus 4 times 11. Good so far? Awesome. And then what? Well, we're going to put A22 at the top left, so that's 7. -1 will be at the bottom right. And then we'll apply the negative to the other entries. Cool, cool? And so what will we get? A inverse will be, so the denominator is going to be -7 minus 44. So, oops, -51, like we discovered up top there in one of our examples. So bringing that in to the matrix, what will we get? -7 51st, +4 51st, and then +11 51st, and then +1 51st. And that will be our result. Okay, so let's take a look at the matrix B. Again, this is one that we already found the determinant for up here, remember? So the matrix B, its inverse now is going to be, B inverse will be 1 over the determinant, which was what? 192, times, what do I do with these entries? Awesome, swap the main diagonal entries and then apply a -1 to the other entries. And then we will get B inverse is equal to what? When we reduce, we'll get 5 over 96, and then 1 over 64, awesome, 1 over 32, and 7 over 64. Cool, cool? Very good, very good. Okay, definition of minors and cofactors of a matrix. So this next definition is extending our skills to be able to find the determinant of a square matrix of order greater than 2. So 3 by 3 matrices, 4 by 4 matrices, etc. So we'll be learning how to do expansion by cofactors. So here we go. If A is a square matrix, then the minor, which is denoted capital M-I-J, of the element Aij, is the determinant of the matrix obtained by deleting the ith row and the jth column of A. The cofactor, which is denoted C, capital C-I-J, is given by C-I-J equals -1 times the minor of Aij. Groovy? Okay, so here we go. Example 2, find the minor and cofactor of A12 and B13. Find the minor first. So M12 is equal to, I go to the element or entry A12. Good so far? A12 is this one here. And so I'm supposed to delete this row here, the first row, and the second column. And then what will I find? The determinant of A21, A23, A31, A33, and what will that equal to? Beautiful. A21, A33 minus A23, A31. Cool, cool? So next up, we need to find the cofactor. So the cofactor for entry A12 will be beautiful. You just raise -1 to the sum of I plus j, and then you multiply that to the minor for entry A12, and what will we get? So this is going to give us -1 times, what was the minor of entry 12? Beautiful. A21, A33 minus A23, A31, which is equal to, I'll switch them around to make it look pretty, A23, A31 minus A21, A33. Cool, cool? And then just kind of matching up what we had found, our minor for entry A12 was equal to this here. All right, now let's do one with regular numbers. So when we want to find B13, let's check it out. For this matrix B, M13 is equal to what? Awesome. The determinant of the matrix, well, let's check it out. 0, 1, 3, -2, which is equal to what? Beautiful. We'll have 0 times -2 is 0, minus 1 times 3 is 3, and that gives us -3. Groovy? Now, C13, the cofactor for entry B13 will be -1 raised to the 1 plus 3 times the minor of the B13 entry. So that was what? Good, -3, so I'll put that in place of the minor. -1 to the 4th is just +1, and so this gives us a result of -3. Cool, cool? So what do you notice? When you add I and j, you're either going to get what? Beautiful, an odd number or an even number. An odd number or an even number. So there is a shortcut to find the sign of your minor. And what that is you can just start at the top left and go plus, minus, plus, because B11, that sign for the cofactor would be -1 to the 1 plus 1. 1 plus 1 is 2. So I plus j is even in entry B11. It's odd in entry B12. It's even again in entry B13. And so it alternates like this. And so all you need to do, this is a real quick way of figuring out what the sign on your minor is going to be. All right? Definition of the determinant of a square matrix is if A is a square matrix of order n greater than 2, then the determinant of A is the sum of the entries in the first row of A multiplied by their respective cofactors. That is, the determinant of A is equal to the other notation for determinant of A, which is equal to the summation from j equals 1 to n of A1j, and then which is the entry you're on, and then the cofactor for that corresponds to that entry. this one would end up being A11, C11, plus A12, C12, and then all the way down until you get to A1N, C1N. Now, what you're going to find out is you can pick any row or column, but we'll show you that in a moment. So for this example, this actually works for 2 by 2 matrices, but it ends up being kind of like a so easy it's hard thing. So here, if you were to take a look at A equals A11, A12, A21, A22, what's going to happen? Well, if I decide to expand about the first row, all right, that means what? I'm going to end up with 2 terms. Okay, I'll be adding 2 terms which consist of the entry times its cofactor. So since we only have 2 entries in the first row, we'll have 2 terms before we simplify. The determinant of A will be, well, first I will expand about A11. And then my cofactor for A11, well, let's see what happens. So here, if I expand about A11, I'd be crossing out the first row, and the first column. Good so far? And then what do we end up with? So the cofactor is going to be what? -1 to the 1 plus 1, so that'll be squared. And then the determinant of A22. Now, coming back, what's going to happen? I mean, you really don't want to actually cross these out. You just sort of do a mental crossing out, because what's next? You're going to be doing what? Beautiful. You're going to be expanding about A12 now. So you'll cross out the first row and the second column to get your next cofactor. And then what's going to happen? Awesome. That'll be plus A12 times -1 cubed, and then times the determinant of A21. That's the only thing left. Cool so far? And remember, look at the signs on the -1s. If I just went here and if I had said, oh, plus minus, that would take care of this part, right? This is a plus and this is going to be a minus. Cool, cool. All right. So anyway, the determinant of A will end up being equal to A11 times A22, because A22 will just be a real number and that determinant will just be itself. And then what? Minus A12 times A21. So we have verified it. Next up, let's find the determinant of B. So I'm going to just start doing the shortcut way, plus, minus, plus, all right? So when I do so, what will happen? Well, first I'll expand about this 2. So temporarily, I'll cross these out so we can see what's going on. So the determinant of B will equal to positive 2 times what? Beautiful. The determinant of 1, 3, -2, 1. And then I am now expanding about the -1. And so cross out the second column and the first row, and let's see what determinant we're left with. Good, so I'll get minus -1, and then the determinant will be 0, 3, 3, 1. And then lastly, let's see what we get. We'll be expanding about this 4 here. And we will have plus 4 times the determinant 0, 1, 3, negative 2. Good so far? Awesomely awesome. Continuing, we will have 2 times 1 minus a negative 6 is plus 6. And then minus a minus 1 is plus 1. And we'll have 0 minus 9 inside to evaluate that determinant. And then plus 4 times, good, 0 minus 3. Continuing, what will we have? 14 minus 9 minus 12, which will give us negative 7. Good, good? All right. And just so you can follow along, these signs here that I'm highlighting in red came from this computation. The entire cofactor part would be positive 1 in this determinant. For the second one, it would be this negative and this determinant. And then for the third one, we'd have this positive and the determinant. And then, so this 2 represents entry B11. This negative 1 represents entry B12. And the 4 represents entry B13. Cool, cool? Now, let's take a look at this more inclusive definition, all right? So, expansion by cofactors. This one is basically saying, hey, you don't have to expand about the first row. You could do the second row, the third row, first column, second column, whatever. So if A is a square matrix of order n, then the determinant of A is given by the summation of A from J equals 1 to n of Aij, that entry, times its cofactor, Cij. So we'll have AI1, Ci1 plus AI2, Ci2 plus dot 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 plus AIN CIN. That's if you're going about a row, the ith row expansion. All right. Next up, the jth column expansion. So now you're going about I. The index of the summation is I. So you'd have A1j C1j plus A2j C2j plus dot 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 all the way down to A NJ C NJ. Groovy? Okay, so let's see it in practice. This is the same example as last time, this matrix B. So what do you think might be an easier expansion? Beautiful. That first column looks good. I'd either do the first column or the second row. If I do the first column, remember this one's positive. The sign on the cofactor is positive for that first entry. So you'd have plus, minus, plus going alternating down. And then let's see what we get. All right. So the determinant of B equals. So when I expand about the first column, I'll be doing what? It'll be a positive 2 times what determinant? Beautiful. 1, 3, negative 2, 1. And I'll write this one out, but in the future I won't. It'll be minus 0 times what? Beautiful. Negative 1, 4, negative 2, 1. But 0 times anything is 0, right? The last one will be plus 3 times its determinant, which is, or the determinant you get when you cross out the third row, first column, which is negative 1, 4, 1, 3 inside that notation. And so again, just to identify everything, this 2 is our B11. This 0 is our B21, and the 3 is our B31. And the cofactors are represented by the signs, right, times the determinants. So you'd have a positive here, the negative comes from that one, and then the positive again comes from here. Groovy? And the rest of the cofactor, of course, is the corresponding determinant you get when you cross out the ith row, jth column. So next step, let's compute it. So this will give us what? 2 times 1 minus negative 6 is 1 plus 6. And then minus 0, that whole thing's going to zero out. And then plus 3 times negative 3 minus 4. Good so far? So we will have 14 minus, and then 3 times negative 7 is minus 21, and we end up with our negative 7. Let me show you another way that a person can compute the determinant for a 3 by 3 matrix. I don't know that it works on any order greater than 3. And you know what? If it did, it would probably end up getting messy anyway. Let's just check out this way. The method that you use is you copy the first and second columns of the matrix to form fourth and fifth columns. So you'll have a 3 by 5. Then you obtain the determinant by adding or subtracting the products of the 6 diagonals. Okay, so this is what you do. When I rewrite B, I have 2, negative 1, 4, 0, 1, 3, and 3, negative 2, 1. So I'm not going to equate I'm not going to say the determinant equals yet, because this is just an algorithm, a way to do it. And then when I recopy first and second columns and tack it on to the end here, what will I get? I'll have 2, 0, 3 going down, and then negative 1, 1, 2 going down. Groovy? Okay, so here's what you do. You go from the bottom left to the upper right. You do each of those diagonal products. So 3 times 1 times 4 is 12. Negative 2 times 3 times 2 is negative 12. And 1 times 0 times negative 1 is 0. And then the next products we take a look at are what? What do you think? Top left 2, bottom right, each diagonal. So that's the first one. 2 times 1 times 1 is 2. Negative 1 times 3 is negative 9. And then 4 times 0 times 2 is 0. We take our bottom sum, so 2 plus negative 9 plus 0, and we subtract from that the sum of the upper products. And that was 12 plus negative 12 plus 0. Cool so far? And so this ends up being our determinant of B equals, and we will have, which will be negative 7 from the first parentheses minus 0, which is, beautiful, negative 7. I don't really care which way you do this. I will have you be doing determinants by hand, because you're going to have to do some determinants by hand when we work on eigenvalues and eigenvectors. Okay? You need the practice. All right. Well, example 5, find the determinant of A and the determinant of B. Why don't you go ahead and pause the movie, work the problem out, and then check to see how you did. Let's see how you did. I'm going to use expansion by cofactors because I just double-checked my notes and I saw that that method that we did before only works for 3 by 3 matrices. It doesn't work for higher orders. Okay, here we go. I'm going to expand about the first row. Again, using our shortcut, we'll have plus, minus, and let's do it. So our determinant of A equals positive 1 times, now we're going to get a 3 by 3. So for the first one, I'll show you what gets crossed out. So when we expand about the entry in the first row, first column, we get this resulting matrix here. So 7, negative 1, 0, negative 1, 2, 5, and 5, negative 8, 7. Cool, cool? And so next up, what are we going to be doing? Beautiful. We'll be expanding about the 0. Do you see that's just going to be 0 no matter what the determinant ends up being? So I'm just going to write minus 0. Now when we expand about the entry in the first row, third column, we will get plus 2 times. So when I circle the 2, cross out the first row and the third column, what's going to happen? All right, so here we go. And then finally, our last one will have a minus 6 times the 3 by 3 determinant consisting of, circle the 6 here, cross out first column and first row. My resulting 3 by 3 determinant will be 3, 7, negative 1, 6, negative 1, 2, and negative 3, 5, negative 8. Cool, cool? So how'd you do? Awesome. I knew you could do it. Okay, so now let's take a look at part B. Wow, this is going to be nice, isn't it? I think expanding about that first row or third column would be ideal. So I'll just do first row. Let's see what we get. So the determinant of B will be equal to positive 6 times the determinant, what? 1, 0, and then negative 2, 11, minus 0 plus 0. Cool, cool. And then that's going to be 6 times 11 minus 0, which is 66. Cool, cool? That was easy, huh? Hey, let's look at something else. So note that the product of the entries in the main diagonal is what? Beautiful. 6 times 1 times 11, which happens to also be 66. What do you think that means? Well, it looks like the determinant, and what kind of matrix was that we were working on? Beautiful, a triangular matrix. So it looks like the determinant of a triangular matrix is the product of the main diagonal entries. All right, so let's make it official. Determinant of a triangular matrix. If A is a triangular matrix of order n, then its determinant is the product of the elements or entries on the main diagonal. And symbolically, we would have the determinant of A would be A1, 1 times A2, 2 times A3, 3, ... all the way down to times AN. Groovy? All right. All right, so for example 6, we want to find the values of lambda. So this here is lambda, the Greek letter, for which the determinant is 0. And I'll tell you a secret. This is actually how you find the eigenvalues of a matrix, okay? So here we go. we want to find the values of this where the determinant is 0, correct? So I'm going to go ahead and equate this to 0. And then we just multiply lambda minus 1 times lambda minus 3, and then minus 1 times 4 is 4 to evaluate our determinant. The right-hand side is still 0. And then we have to expand this out, so don't forget about your algebra skills. You'll have lambda squared minus 4 lambda plus 3, and then minus 4 is 0. And that will yield lambda squared minus 4 lambdas minus 1 is equal to 0. Cool so far? All right, well, how would we solve that? Beautiful. You can just use the quadratic formula. You could complete the square, use your calculator, whatever. I'll just work it on out. So lambda would equal to negative 4 plus or minus the square root of b squared minus 4 times a times c over 2 times a for our quadratic formula, and then lambda will equal to 4 plus or minus, that'll give us 16 plus 4 is root 20 over 2. Simplifying root 20, you get what? 4 times 5 is 20. So we'll get 4 plus or minus 2 times root 5 all over 2. And that in turn simplifies to be lambda equals, beautiful, 2 plus or minus root 5. So what we could say is lambda 1 is 2 minus root 5, and lambda 2 we can call 2 plus root 5. Cool? Let's take a look at this next matrix. So here we have what? Just a regular old matrix. It's named A, and I'm thinking if we find the determinant of this, let's go ahead and expand about, let's see, maybe the second column. Does that look all right? So that would give us, we'd have a plus, minus, and then alternating down, we'd have that. So finding the determinant, we would have -2 times 3, -1, 1, 1, the determinant of that. And then plus 4, and then times the determinant of -1, 1, and then 1, 1, minus 0. The other one will zero out. So our determinant of A will end up being -2 times 3 minus -1 is 3 plus 1. And then plus 4 times -1 minus 1. And that in turn will give us what? -8 minus 8, which is, beautiful, -16. Now, let's look at the same determinant, okay, that we had in the last one. And I'm gonna row reduce that determinant and make it triangular, okay? And so let's see what happens. All right, so A was equal to -1, 2, 1, 3, 4 is -1, and 1, 0, 1, okay? And so I want to make a triangular matrix, right? So to do so, I'll go ahead and just do it like we regularly do, get the bottom 3 zeros, okay? So our first move would be to do row, 3 row 1 plus row 2 for a new row 2. And that in turn will give us, beautiful, we'll rewrite row 1 and row 3. And our new row 2 will be -3 plus 3 is 0. And then 6 plus 4 is 10. And 3 plus -1 is 2. And then we'll have, what do we want to do next? Let's just do row 1 plus row 3. And that'll give us a new row 3. So we'll have -1, 2, 1, 0, 10, 2. And our new row 3 will be, good, -1 plus 1 is 0, 2 plus 0 is 2, and then 1 plus 1 is 2. Okay, so next up, if we say negative row 2 plus 5 row 3 for a new row 3, we'll get our next desired 0. So let's see what we'll have. We'll have a 0 here, we'll have a 0 here, and then what's going to happen? We'll have -2 plus 10 is 8. And we're all done. Cool, cool. Okay, so I had an evil plan. All right, so let's call this matrix B, this row reduced form of the matrix. So what's the determinant of matrix B? Well, we know from our theorem about triangular matrices, it's going to be the product along the main diagonal, so -1 times 10 times 8, which is equal to -80. Cool so far? Okay, so let's see, -80. Now, let's think about this. The determinant of B, can we write it somehow related to the determinant of A? So just as a reminder, we got -16 for the determinant of A, okay? And so it turns out that the determinant of B is equivalent to 5 times the determinant of matrix A, right? So, maybe there's something cool about that. Let's check out this next theorem. 3.3 says elementary row operations and determinants. Let A and B be square matrices. When B is obtained from A by interchanging or swapping rows, then the determinant of that matrix B is equal to the opposite of the determinant of A. Now, when B is obtained from A by adding a multiple of a row of A to another row of A, then it turns out that the determinant of B equals the determinant of A. So let's clarify this one. That's when your new row, the one we always write in purple, is not scaled. But the other row that's just temporarily changed to get the new row can be scaled. If the new row is scaled, you also need to use this third one. So the third one says when B is obtained from A by multiplying a row of A by a non-zero constant C, it turns out that the determinant of B is equal to that constant times the determinant of matrix A. So also, this theorem remains valid when the word column replaces the word row. So operations performed on columns are called elementary column operations. Groovy? So let's see what we did on each of these, okay? So on our first iteration here, we multiplied the non-changing row by 3, added to it row 2, and got a new row 2. And so at this point, the determinants are unchanging. So in this case, it would follow rule number 2 from below. Cool? Now, let's see what happened. On the next one, which rule does that follow? Beautiful. Rule number 2 again. So the determinants, rule number 2. So the determinants haven't changed, right, with what we've done. Now, what happened here? We multiplied row 2, so I'm looking at this third operation we did. We multiplied row 2 by a negative, and that's not going to change anything because it's row 3 that's changing. But what did we do to row 3, which is going to be the new row? We multiplied it by 5. So at this point, we applied rule number 3, correct? And so that is why the determinant of B is equal to that constant 5 times the determinant of A. Pretty groovy, huh? Now, think about this. If you're using a determinant in coding, if you want to, reduce the number of operations so your program runs more smoothly, then it's worth it to row reduce the matrix a bit beforehand. Cool? Okay, so now let's look at this example 7 and determine which property of determinants the equation illustrates. So this first determinant, right, is equal to what? What happened here? Beautiful, the column switched, right? So column 1 and column 3 were swapped, right? And so this was property 1 applied. Cool? Okay, so what happened with part B? Looking at this one, let's see what it looks like. I mean, do you see that this one is like 2 times 1, 2 times negative 2, and 2 times 1 for that first row. And then look, 2 times 3, 2 times 5, and 2 times 1 for that second row. And then, wow, 2 times 2, 2 times what? Negative 2, and then 2 times 3 happened to that third row. And so this is why you've got an 8 here, because you end up getting 2 times 2 times 2, which, and then that's multiplied to, the 1, negative 2, 1, 3, 5, 1, and 4, negative 2, 3. So going from, one to the other, it turns out that property 3 was applied multiple times. Three times. Cool, cool? Now let's take a look at this next example. Use elementary row or column operations to find the determinant. So, all right, let's check it out. Go ahead and pause the movie, work the problem, and see how you do. Okay, let's see how your result came out. So for my first step, I'm going to go ahead and take -4 row 1 plus 3 row 3, for a new row 3. This will give us the matrix of 3, 8, -7, and then 0, -5, 4. And then my new row will be 0, because -12 plus 12 is 0. -32 plus 3 is -29. And then 28 plus 18 will be 46. Cool so far? Okay, next step we'll have -29 row 2 plus 5 row 3 for a new row 3. This will give us our 0 will stay here. We'll have a 0 here. And then when we do -29 times 4 plus 5 times 46, we're going to end up with what? 114. And that will equal to our B matrix. So let's see what happened. So for our very first operation, was our changing row scaled? Beautiful. Yes, it was, right? It was scaled by a factor of 3. We've got that going on. So for the second one, was our changing row scaled? Yes, it was scaled by 5. Cool so far? So it turns out that the determinant of B is going to equal to 3 times 5 times the determinant of A. Cool so far? Well, we can find the determinant of B, right? That would be our unknown. So the determinant of B will be 3 times -5 times 114. That's going to equal to 3 times 5 times the determinant of A. And so we will have 1710 would equal to 15 times the determinant of A. And then dividing both sides by 15, we'll end up getting what? 114. I guess I could have seen that before I multiplied it out. And that'll actually be -114 is equal to the determinant of A. All right, conditions that yield a 0 determinant. So if you have an entire row or column that consists of zeros, then you could expand about those zeros and you'd get a 0 determinant. If 2 rows or columns are equal, well, then you could end up getting a row or column of zeros, right? and then thus a zero determinant. Thirdly, what do you think? If one row or column is a multiple of another row or column, cool? Okay, so check this out. This next part is the number of operations. So again, thinking of coding. So if you have these are matrices, square matrices of order, whatever, order n. So the first one is a 3 by 3. So if you end up doing just the straight up cofactor expansion, you've got 5 additions and 9 multiplications. All right. Whereas if you do the row reduction first to get something triangular, you would have 5 and 10 respectively. So that's not much different, right? It might actually be faster to do the cofactor expansion. But okay, let's look at order 5. Order 5, you'd have 119 additions and 205 multiplications if you did it the regular way. With row reduction, you'd only have 30 additions and 45 multiplications. So that's getting significant. And look at if you've got a 10 by 10 matrix. 3,628,799 additions and 6,235,300 multiplications versus the row reduction would just be 285 and 339. So that's just trying to show you that this is really worth learning, especially if you're going into computer science. Cool? All right, so now let's prove this property. So here we just really need to do this via algebra. And it won't really matter what you expand about, honestly, but it's up to you. Go ahead, pause the movie, see how you do. All right? Okay, let's see how you did. I'm going to expand about the first row, and then we'll have, for our left-hand side, positive 1 plus a, and then we'll have the resulting determinant 1 plus b, 1, 1, 1 plus c, and then minus 1 times the determinant 1, 1, 1, 1 plus c, and then plus 1 times the determinant 1, 1 plus b, 1, 1. Cool so far? Awesome. All right. So then that will equal to 1 plus a, one plus b times 1 plus c, minus 1, minus 1 plus c, minus 1, and then plus 1 minus quantity 1 plus b. Cool? Okay. So here we go. We will have 1 plus a times 1 plus b plus c plus b times c. Cool? Minus 1 plus a times 1 is quantity 1 plus a. I'm going to do the next one. Actually, they'll be shorter. So do you see the 1 0 out? So we'll just get a minus c for the next one. and then a negative b for the third. Cool? All right, so then still cleaning it up a bit, we're going to end up with, we'll have a 1 plus b plus c plus bc, multiplying the 1 throughout. And then we're going to have plus a plus ab plus ac plus abc. And then minus 1 minus a minus c minus b. Cool? Equals bc plus ab plus ac plus abc. Cool? The rest of them zero out. All right, well, we've been given that a, b, and c are non-zero, right? So if I factor out an a, b, c, what will I get for the first term? 1 over a, and then what? 1 over c, and then 1 over b, plus 1, and cleaning it up so it looks just like the right-hand side, we'll have equals ABC times 1 plus 1 over A plus 1 over B plus 1 over C, and we verified it. Groovy? Okay, so that ends the lesson for the day. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe. Bye.